So first we're going to start with electromagnetic induction. But first we're going to do a little bit of revision. We're going to start with magnetism and magnetic fields, the motor effect, and all those associated bits and pieces. So what do you need to remember before we go any further? Well, first, how to draw a magnetic field around a bar magnet. Now what you must remember about field lines is they always point to the south pole. So that is the direction convention, always to the south. You also have to remember that the closer they are, the stronger the field is. So we have a very strong field close to the poles, and as they get further apart, away from the magnet, you get a weaker field because they're separate. Now, as we're getting into a little bit, stuff that's a little bit harder, we're going to call these field lines what they really are. These are lines of flux. So now let's start with some definitions. The magnetic flux density, B, which is a quantity you've come across before, okay, is often called the magnetic field strength. That's what we've called it in the previous chapter when we studied this. The strength of the field, the density of the field lines. And that's why it's also just as appropriate to call it the magnetic flux density. Flux are lines of field. Density is the amount of lines per unit area or volume if we're considering 3 dimensions. So B equals magnetic flux density, but it also equally can be defined as magnetic field strength. The strength of the field, B, is equal to how densely packed the field lines are in that area. And as you can see in this diagram, there are more flux lines per unit area in 1 here than in 2 here. So therefore, the strength of the field in B at 1 is bigger than at 2. Okay, you got that? Now we should also review what happens to a current carrying wire in a magnetic field. Remember, the magnetic field is always pointing to the south. A wire that's carrying current in a magnetic field will experience a force. Use Fleming's left-hand rule now to try and predict which way this is going to move. Hopefully you remember Fleming's left-hand rule, and the first finger points to the south because the first finger is the field. Yes, they both start with F. Fantastic. The second finger, if you think about that, C, is the current. And remember, it always refers to the conventional current, which is usually represented as an arrow anyway, but always point in the direction of the convention, which is as if it was a positive charge. So in that case, moving towards a negative pole. Okay, so have a think now, which way is it going to move? Now I'm hoping that you worked out using your brain that this goes up. Okay, so that's your upward movement. Let's have a look at why that happens. What you must remember is that you have got 2 magnetic fields acting with respect to each other. So you've got the magnetic field lines due to the bar magnet. Those are the green lines that you can see there. And then secondly, you have the magnetic field around the current carrying wire that's going through the center. So you should remember that if you have a wire carrying current, there will be a magnetic field traveling around it. Now, how do you predict the direction of that magnetic field? Remember, you need your right hand rule. Right hand, basically you just have a thumbs up and your thumb points up and your fingers curve round like that. If not, you might have to do a little bit of revising. So depending on the direction of the current, your thumb either points up or it points down and it shows you the direction. So in here, what we have is we have current coming out of the screen, and if you use your right hand thumb rule, you will see that the direction of the magnetic field is counterclockwise. And so underneath the wire you have these two magnetic fields, the magnetic field due to the wire plus the magnetic field due to the bar magnets here and here are in the same direction, whereas in the top part they cancel out. You can see that the green line is pointing that way and the blue line is pointing that way. So you have an area above which cancels and an area below which superimposes, and the resultant movement is up. And here you have Fleming's left-hand rule fully explained with a much better picture than what I drew for you a few minutes ago. Okay, so the thumb points upwards, first finger is the field, always pointing to the south, the second finger is the current, which is out of the paper there, and shows conventional current. So let's have a go at some questions, a few revision questions here. So the first question, in which direction is the force on the wire? Let's have a look at the direction of the current flow. Remember, this is conventional current. The tall line of the battery represents the positive terminal. So conventional current would be moving away from that. If that's the positive terminal over here, then a positive charge would move away from that. And so the current flow is in this direction. So if you use the left-hand rule with current flowing that way, your second finger would point that way, your first finger would point that way into the paper towards the South Pole, and you should then work out that you have a movement upwards. Now what's sneaky about this question is the setup is slightly different to what you're used to. The wire is fixed, okay, and what you can move, however, is the magnets. So what's happening is the wire is experiencing a push up, right? But the wire can't move. So what the wire is doing to the magnets is it's pushing it down. It's like a Newton's third law question. If the magnetic field is producing a force upwards on the wire, then the wire will produce an equal and opposite force down onto the magnets. So that means that the balance gets pushed down, and that will register a reading on the digital balance here. So for the next bit, when the current starts to flow, the balance indicates there is an extra mass. So here we would register a mass of 4.2 times 10 to the minus 2 G. So if that's the mass, the equivalent force would be mg, which would be this value times 9.81 to give you the weight, the actual amount of force pushing down. And then lastly, if the current is 1.64 amps and the length is 8.13, you can see that there's no complication with angles. The length of the wire is perpendicular to the direction of the field, okay, because the field is going that way and the wire is perpendicular to it. This is not exactly a great diagram for that, but you should be able to tell that it's perpendicular. So we're just going to use the equation for this theory, which is BIL, with sine of the angle equal to 1. Okay, so you just substitute your values in there for current and length. Remember, centimeters, no, we want meters. And you should be able to get a value of B. So the next bit I'm going to talk about is the actual generation of electricity, and I'm going to review again how that takes place in a steam powered power station. Now, depending on what the initial fuel is, so you could have coal, gas, or even nuclear, but what we start off with is fuel generating heat. Okay, so in the case of fossil fuels, the fuel is burnt and that heats the water to make steam. The steam then, which is a very high pressure and has the particles have a lot of energy, they turn the turbines here, okay, which turn a generator to produce electricity. Now that is what we're going to be talking about now, and in fact later on we're going to be looking at the rest of the electricity generation process, which is the transformer. That's easy. Okay, and a little bit on how to make this kind of electricity, which is AC, how to turn it into something which is a little bit more appropriate for daily use, which is direct current and DC. But all of that will come later. Let's have a look at this idea of the generator. How do we actually make electricity? The basic premise behind the generator is really familiar to you already. This picture, once you get over the initial panic, should look a little bit familiar. It's the motor. Or is it? Well, we'll see in a minute. But what you should remember about the motor is that you put in an electric current. Okay, so this is your input electric current. And because this electric current, this current carrying wire, was inside a magnetic field, then as if by magic, it would start spinning, right? You would get rotation clockwise, because that's what happens. If you get current plus a magnet, you will get movement, which is crazy when you think about it. Now, a generator is almost exactly the same, but there is a very basic difference. In a generator, what you put in is movement. You actively have to start spinning the coil inside the magnetic field. And because of the presence of that magnetic field and the coil moving within it, every electron would start to feel a push. And because the electrons all feel a push together, what you end up getting is a generation of flow of charge, a current. Okay, so this current would actually start to flow in this direction. However, as the coil starts to move down out of the field, as soon as it's there, it will stop. And what you'd end up is having like an increase in current and then a decrease. And then as the coil moves up here again, it will experience like a maximum flow, but in the opposite direction, the other way around. And then as it spins up to here, it would end up with no current at all. So that's a lot of things to get your head around. So we're going to have to go through that bit step by step, I think. If we start, what makes a dynamo or a generator? Dynamo and a generator are pretty much the same thing in terms of the scientific principle behind it. So what's going on in a generator? You put in movement plus magnet, and you get out current. Okay, but it's pretty much the same machinery. Now what I do recommend is you have a look at some of the videos on the site which show you some really good simulations of this, and you can see how the current flow varies depending on the position of the coil. So that would be a really good thing to do now. So here's some further revision for you. See if you can remember how to work out the electric field strength in a uniform field. There's actually two relationships for that. And then go back and review what the force on a single charge on a magnetic field feels. Stop the video and see if you can find this information. The electric field strength in a uniform field can be found on parallel plates, where you might find a positive and a negatively charged plate, and an equally spaced set of field lines. Okay, here's another bit of revision. They're equally spaced because the field strength is the same everywhere, and they point down towards the negative plate because the convention, remember, is for a positive charge moving in the field. Okay, so that's that. How do we work out the electric field strength? It could either be the force per unit charge or the potential difference across over the distance between the plates. Okay, so that's a little bit of revision for you because we'll be using this a little bit later. In terms of a force on a charge in a magnetic field, you might remember, if we have a magnetic field into the paper, as so, represented by these crosses, remember this is the back of an arrow. The back of an arrow is a cross going into the paper, and a dot would be coming out of the paper. So if we have a field like this and a positive charge flies in like this, okay, what's going to happen to it? So you can use, once again, the left hand rule to predict which way it's going to move, which way the force on that wire is going to act. So we have the magnetic field pointing inwards, okay, so your first finger will go in. You have your current finger, your second finger, okay, pointing in the direction of the positive charge, because remember, the second finger is current and it's a conventional charge. And then you have the thumb pointing up, okay, and that's what you should see. You should see that there is a force acting up, which means that this charge will continue moving in a circular path. Why is that? Very common question, because the movement, which is in this direction, and the force acting on it are at 90 degrees to each other. And this would continue as the direction changes anyway. It will always be at 90 degrees. Okay, so we've gone off on a bit of a tangent there. So just to remind you then, we have a moving charge in a magnetic field. You can use the left-hand rule to predict the way it's moving. You've got to be careful that you are using a positive charge for the left-hand rule. If it's a negative charge, you're going to have to point the other way or use the right-hand rule. It's up to you, okay? But we'll have to revise this a little bit more somewhere else. This is just a bit of background. Now, what is this to do with the relationship force? Well, you should remember now then, the relationship for force is BQV sine of the angle, and we'll talk about that in a minute. By B, we're talking about field strength, the magnetic flux density, or the field strength. Q is the charge on the particle, the speed of the particle, V, and sine is the angle between the direction of the motion and the magnetic field. Okay, so let's have a look at what that's got to do with induction. So this is how we derive an equation for the induced EMF, this produced EMF in a straight conductor in a uniform field. So this is our uniform field. Our magnetic field is pointing into the paper. As you can see, it's a cross. Shoot an arrow down into the paper. Okay, and you have a movement. So let's just focus on this charge here. Let's imagine that we don't have a wire anymore. It's just a single positive charge moving this way. Now, if you try the left-hand rule and you use your current finger as this way, okay, moving down, so this would be your second finger, and your first finger, your field finger, is pointing into the paper, then you should be able to tell that your thumb, all right, is showing you a movement in this direction. Okay, just check that out. So your first finger is moving in Okay, it's pointing in, your second finger is pointing down, and your thumb is pointing that way. Now, this is assuming that the charge is positive, right? But it's not in this picture, so I don't want to confuse you too much. Because the diagram is talking about a free electron, right? Not a positive charge, then the movement would be in this direction. Okay, so what's happening here? What you're doing is you're seeing that there is a push of negative charges in this direction. So this will accumulate negative charges. And this side, because it's losing negative charges, it's becoming super positive. Now, what does that mean? We've got a difference in potential, right? We're creating an electric field. Now, it's that electric field which causes the current flow. It gives us this EMF, this potential difference. Okay, so let's put that into some kind of an equation. So let's have a look at the equations. What is the force that is pushing the electrons in this direction? Okay, well, we have used it before. It's QVB, or BQV, sine the angle between the flow of electrons and the magnetic field strength. But that gives us the push in this direction. And that force in that direction, we'll see, is also equal to the eventual force due to the electric field. So we have a magnetic force which is equal to the electric field, the force due to the electric field that it then produces. Assuming that the angles are perpendicular, there is no need for sine of the angle. BQV, which is equivalent to the magnetic force, is equal to the force due to the electric field. Now, let's do a little bit of a side step here. The electric field strength is equal to the force per unit charge. Right, by force we mean the force on a charge that's moving within that field. And it's also equal to the potential difference across the plates, or the position, over D. Okay, so we're just going to rewrite these two quantities. The potential difference that is produced is going to be the EMF, which will eventually lead to the current that's going to be generated. So by potential difference, we mean EMF in this case. And by distance, we mean the length of the wire. Okay, because that's how far it's going to move. That's how far the charges are being pushed to the side. So these two are equivalent. Should know from our electricity topic, potential difference voltage could be either a potential difference or an EMF. In this case, it's an EMF because it will lead to a current being generated. And here we have a distance which is equal to L, a length of wire. Okay, so if we rearrange that, what is our electric force equal to? Our electric force is equal to E over L times Q, okay, by rearranging these four quantities. Okay, so now you can see why our electric force here is equal to the EMF times the charge times the length of the wire. Now if we rearrange that, we end up with a simplification. Let's have a look. We have Q on both sides, so we can get rid of Q. And if we write this in terms of the EMF produced, we end up with B VL. Okay, which is on here. So this will give us a measure of the EMF produced when a current carrying wire of length L in meters, moving at a speed of V in meters per second, across a magnetic field strength of B in Teslas. Now you must be careful with the units when you're answering numerical questions. Talking of which, so now apply that formula to the following question. What EMF is produced across a 23 centimeter long conductor moving at 98.0 centimeters squared, perpendicular across a magnetic field strength of 120 micro Teslas? Have a go. Just some things to look out for. Teslas, if you go out and define it and do your unit analysis, will take you back to meters. So make sure that you change the 23 into meters, the 98 centimeters per second into meters, and use times 10 to the minus, take a guess, 6. It's micron. Okay, so have a go. Okay, and this is a very straightforward question. 2.7 times 10 to the minus 5. And here are a few practice questions. They don't have any tricks to them, so I'm not going to help you with them because they should be okay. If you find any of them particularly difficult, just send me a quick email and I can send a little video tutorial. But it's just using the previously defined formula. Okay, so that should be enough for a little mini lesson for today. I might post another one later on today or tomorrow morning. So have fun.